Let's look at one last example because we're talking about rates of change. We say velocity is the rate of change of position, but we find that there is a rate of change of velocity as well. The rate of change of velocity with respect to time is called acceleration. So if I can find the velocity given information about the position of my object or bicycle or particle or whatever, can't I find the acceleration if you give me information about the velocity? And I can. Suppose that the velocity at time t of a particle is given by this function v of t equals 2t squared. I want on a side note to talk to you about a particle. The BC exam in May is full of questions about motion. That's the power of calculus. The power of calculus is that we can talk about what's happening to things in motion on the face of the planet. So the people that write the test love to give you position, velocity, or acceleration of a particle or an object. So particle, they love particle motion. They love object motion. They may give you some sort of specific thing that is moving. Might be a squirrel bouncing along a power line. It could be anything. But by and far, they love particle and object because it keeps things conceptual. And they find that students get confused when things are conceptual. So we're going to have a lot of particles moving. We're going to have a lot of objects moving. Know that they have to follow the mathematics just like the squirrel bouncing along the power line does. So the fact that it's a particle moving, I don't want that to bother you. You're going to see particle motion and object motion enough that I think you'll get comfortable with it. So back to the problem. Suppose that the velocity at time t of a particle is given by v of t equals 2t squared. Find the instantaneous acceleration at one single point, one single input value. I want to equate some things. We're going to start moving along with our knowledge of notation here. Given the function f of x, we call the derivative function f prime of x. Here they're calling the derivative function acceleration. We'll call it a of t, but understand in context that is the derivative of velocity. We could equally call that v prime of t. We're going to use the definition of the derivative to find what the instantaneous acceleration is when t equals 1. So here is v of t. For us, now our notation has changed. We're going to find v of t plus h, the same as f of x plus h in this context. We're going to subtract from that v of t, equivalent to that function, still all over h. So let's fill this limit out. The definition of the derivative using this velocity function is 2, open parentheses, same process, even though the functions look different. Same process. My process was to take the original function as given, write open parentheses where it had an independent variable. For us here it's t, and the other problem it was x. Now what I'm going to do, everywhere that this function has a t, this function has a t plus h. And now I have filled out the definition of the derivative. This result will be v prime of t, equivalently written as a of t, or acceleration. So the limit as h approaches 0, I'm going to FOIL that out. That's t squared plus 2ht plus h squared. I'm not doing too many things at once. I can distribute that through quite easily in another step, and that way I don't make an algebra error. We are going to hop down here and finish evaluating this limit. So I have 2t squared plus 4ht plus 2h squared minus 2t squared all over h. I'm going to clean up what I can. A positive 2t squared minus 2t squared, those two things cancel. Every other term in the numerator has an h in it. That's what I'm after. So I have h times 4t plus 2h all over h. Wonderful. Now I can take h to 0. The acceleration of this function at any time t. I have found a of t for every t value you might ask me about. This particular question asked me about when t is 1. So if I have found the acceleration function for any input value, I can certainly use it to find the acceleration at the given t value that they're asking for. And the acceleration here is 4. And if they gave me units, I would need to include the units. It's seconds. They did not tell me whether it was meters or whether it was feet. I don't know what that measure is. So we would just say units per second or per second squared. There are some examples of evaluating derivatives, slope of the tangent line, at one single point as opposed to 2 points for average, instantaneous rate of change. In the context of position, that instantaneous rate of change is velocity. We're going to have lots of context and lots of different types of derivative functions. But for our next homework set, you need to be able to evaluate the definition of the derivative and find either the derivative function and or evaluate that function at a given input value, like this example asks us to do.